In this presentation, I'll present the power of sound. Audio reactive video generation with stable diffusion. In recent years, video generation has become a prominent generative tool and has drawn significant attention. Specifically, text-driven video generation method is the most popular tool. However, it may be challenging if users want to drive it into more complex sequential procedures. Furthermore, it faces difficulties to represent the different scale of magnitude in the text-driven generation. Compared to text modality, audio modality contains unique qualities like temporal semantics and magnitude. However, there is little consideration in audio to video generation until now. Furthermore, most of the existing audio-driven video generation methods did not fully utilize the unique quality of audio modality as shown in the table. Our contributions are summarized as these. We propose a novel sound-driven video generation method built upon stable diffusion. Our attention-based audio encoder produces temporally aware latent vectors to produce audio-reactive video frames, preserving identity throughout the generated video. Our model outperforms other baselines. The figure represents the overview of our proposed model. Our model consists of two main modules. First, audio encoder, which produces a sequence of latent vectors, encoding temporal semantics of audio input by utilizing clip space and highlighting the important temporal features. Second, audio semantic guidance module, that generates video frames that are temporally consistent and audio reactive. In this section, we introduce the method how to train our audio encoder. Audio inputs are first transformed into a MEL spectrogram representation. To incorporate time information, the MEL spectrogram is divided into n segments. Each segment is then fed into a shared feature extractor module, and the feature extraction module learns to extract low-level features from each audio segment regardless of its time dependency. As our goal is to generate audio-reactive video frames, it is also important to encode temporal changes, or relations, of the given audio inputs. We apply the standard long short-term memory, LSTM, network to encode temporal relations or changes between consecutive audio features. Given the pre-trained image text pre-trained clip model, we apply the following info NCE loss in order to align audio semantics with clip space. Also, we applied spec augment method to the audio data and add the info NCE loss to pull augmented audio features together. We further use an attention-based module to encode temporal semantics from the audio inputs as shown in figure. Temporal attention module is denoted as TAM. We empirically observe that adding this module helps improve the quality of video frame generation. It is because model becomes flexible to focus on more important temporal information, improving the model's representation power of the magnitude of audio sound. Here, the figure represents the ablation study of temporal attention module, TAM. The figure represents generated video frames with and without our temporal attention module. We generate video frames with splashing water sound where its amplitude changes over time. We observe in the figure that our model is indeed able to generate video frames reactive to the audio changes over time. Lastly, in mapping module, we align the audio embeddings with the text sequence embedding in the stable diffusion. This module maps the audio embedding to the latent space of stable diffusion. We use two audio-video datasets to train our audio encoder, VGG sound and landscape. Table shows the evaluation results with those metrics. It demonstrates that our approach produces the best quality results as video, and it shows a superior performance in terms of multimodal semantics. Furthermore, we conduct a user study with 100 participants. Participants are shown generated video frames and asked to evaluate them in terms of realistic, vividness. Also, consistency, and relevance between video and audio in 5-point scale, that the higher score is better. The results, shown in figure, demonstrate that our proposed method outperforms other state-of-the-art approaches. We also qualitatively evaluate the quality of generated video frames. In figure, we provide typical examples of generated video frames by existing audio-driven video generation methods and ours. Note that Sound 2 Site and CCVS need the initial frame as input, which is denoted as red boxes. Compared to other baselines, ours generate a scene of a waterfall or a fire-on-fire crackling, aligning well with audio inputs. Next, we provide examples where audio inputs are changed. As we observe in figures, our model successfully adapts to the audio change, generating video frames accordingly. This may confirm that our model is indeed conditioned on the audio sequence and can generate audio-adaptive video frames. Furthermore, as our model is built upon the stable diffusion model, it is also possible to use text and audio as a condition together. In conclusion, in this paper, we propose the power of sound, a novel audio-to-video generation with stable diffusion. Our work extends the usage of audio modality on generation models, and broaden the methods of using stable diffusion by generating realistic videos by our audio encoder. Video examples are provided in the project website. Thank you for listening.